Okay, so now is the Logistic Regression Module 2. We're going to focus on training and optimization. Okay, so how do we train a logistic regression? What type of loss formulation? So in the previous section, we covered the representation. The most important representation is the PC conditional X, and in the logistic regression case, we actually simplified it into P y conditional 1ix because it's a binary variable. We only just need to estimate this, right? So again, to repeat what we had, just to give you a kind of review, reminded view, I mean, this is like beta transposition x over e beta transposition x plus 1. So this is how my logistic regression looks like. Okay, so I have the representation, and then how do I measure the loss or the cause? So when you have this kind of probabilistic formulation, the most natural way is in fact the likelihood function. We actually reviewed about maximal likelihood estimation, and I hope you still remember a little bit is you are given the samples, and what we reviewed is the basic Bernoulli case. It's just heads and tail. You actually see many observations of those flipping the coins, and you got a set of flipping coin outcomes, and we represent them as z1, z2 until zn. And then in the basic Bernoulli case, we try to use that to estimate p hat. And the way, to construct this function, this is actually likelihood function, is just you try to estimate the joint probability of pz1 until zn, and in this case, we can write it, the theta in the basic Bernoulli is our p hat. And because they are, like I mentioned in the beginning, the majority of the machine learning method, assuming samples are IID, independent, identically distributed, which means they are independent. And when they are independent, the joint probability is just each factor's probability multiplied together. That's exactly how you use it. And then the whole question is, how do I estimate PZI conditional on theta? For a specific sample, what is that probability formulation, right? And this is the basic MLE. It's not just for logistic regression. Whenever you have this probabilistic formulation, you have a parameter estimate, and then you use this as a protocol, right? So we actually had a detailed review is you need to be very clear who is your unknown parameter. In the Bernoulli case, is p hat. And then also who are your observed samples, z1 until zn. And also the most cases, we don't directly work with likelihood because, this is a probability, right? Once probability, it's within 0 and 1. And then, so hopefully not 0. If anything is 0, no matter how many samples you observe, that whole multiplication is 0, right? That's just first alert. And then hopefully you don't have a 0 probability, but when they are all very small, when n is pretty large, let's just assume 30,000 samples. Think about 30,000 probability measure multiplied together. That quickly reaches the numerical ability your computer can represent. So that's the reason why people normally work with log probability, because this is a much better numerically stable measure. All right, so this is what we covered last time. So we did not go to here, to touch how do you do basic MLE for basic Bernoulli. So I hope your probability entry level class already covered that. So I will do a really quick walkthrough about this. Again, so we observe the outcome HHTT, so many from our observed n samples. we can just write them as 1, 0, right? I mean, it's just numerically easier. And like we emphasized in the basic MLE, the most important to get that, the most important to get that joint probability formulation is to have each PZI condition on theta. So how do you write PZI condition on theta? So here, I hope you still remember how to write probability for Bernoulli distribution. So this is my P hat. The P hat, so if it's a head observation, the probability should be P, right? If it's a tail observation, the probability should be 1 minus P. And this joint product style is exactly representing summarizing both. So let's just decompose it. 1, your ZI is a head, and the 1 minus ZI part becomes 0, and then what you get is PZI equal to P. When you observe its tail is 0, that give you 1 minus P. So this is really a good summary. This one equation summarizes a Bernoulli distribution. And then my point is I need to get this log likelihood or likelihood, right? How do I get it? Very easy. I really just, let me change to a different color, change to a blue color. And after you have the PZI condition on theta, then you have just consider all the Z1 until Zn. Very simple. You just multiply to get this joint probability. It's argmax. This is your probability. Your parameter is P hat. All right, so this is the I from 1, and then you just multiply I from 1 to n. Okay, so then you just draw as log LP, and then I'm sorry of the background. So, okay, so you have the log LP. You just put the previous page there. You can do a derivation. And then it's very easy because this is multiplication, and then when you take a log, that equivalent to summation of the log of the internal term. And then just very easy doing all these derivations, and essentially you can just maximize that maximal likelihood estimator, and then the equivalent to you minimize the negative log likelihood. And I don't want to do the whole derivation. Very simple, same thing as what we had before. You have a cost function, you set it to 0, and then you take gradient, you take a gradient, you set it to 0. What you're going to get, the best of P hat, is just the summation of number of heads appeared over all possible times you flip the coin. So this is the basic Bernoulli. So I want to emphasize the point is, so what we normally observe in the deep learning is something called negative log likelihood. Which is exactly the likelihood take a minus. So the reason why we use in deep learning called negative log likelihood, because the majority cases is we always think we minimize the loss, right? So likelihood is something to be maximized. So people just flip it to take a negative. To kind of normalize with other MSE laws, 0-1 laws, the other kind. So this is a mostly used loss function in the deep learning classification. All right, so now I told you about basic Bernoulli, how to move from basic Bernoulli MLE estimation to logistic regression. I will not do the derivation, but actually it's extremely almost the same. We just write down the PZI given P, and then we put them together as likelihood LP. The only differences is the P hat now is not a constant anymore. The P hat now changes to this parameterized view, which is the PYI equals to 1 given beta, which is that E beta transposition X over E beta transposition X plus 1. All right, So everything is the same as the basic Bernoulli. The only difference is you replace that p hat in the basic Bernoulli by this parameterized form. Then you can have all the similar derivations, and what you're going to get is actually this form. So here I have a rewrite of notation, something called PYI prediction. So I just rewrite this PYI equals to 1 into YI hat. I mean, that use that as my prediction. This is my YI prediction. And then if I do this kind of notation, what I get is this specific form. So this is the thing. So if you take a minus, this is like summation from I from 1 to n, yi log yi prediction plus 1 minus yi log 1 minus yi prediction. This is exactly cross-entropy. And if you ever took classes in maybe information theorem, you can see very easily the connection of entropy to this cross-entropy. All right, so enough. I mean, you just, again, the same, do the same derivation, go on, and this is what you get, the maximum likelihood or log likelihood that you need to maximize for the logistic regression in training. Okay, so now let's see, we have a loss function, which is the likelihood or log likelihood. So, or maybe let me just make it more standard, is the negative log likelihood. So how do you optimize it? So in fact, the literature, I mean, if you truly just only optimize logistic regression, what you need is, there's actually some method called Newton-Raphson optimization, which is a second-order optimization method. The reason is the logistic regression, that MLE negative log likelihood function, you actually can calculate its gradient form. You can also calculate its second-order hashing form, and which makes it possible to apply the second-order optimization method. But we're not going to cover that. What we're going to cover is the stochastic gradient descent based. All right, so let's see. When we talk about stochastic gradient descent based, what I really want is really opens the door of from logistic regression and then to deep learning. And that's why I put it as the last section of logistic regression, because this is like almost a fundamental to view the deep learning. I think this kind of echoed our third view. Yeah, that's the third view, view 3 of logistic regression we just reviewed. So it's, yeah, I can do H. I actually did H in the previous page. So now I do Z, but kind of it's just a notation. So we treat the first phase, this linear summation, using that as a notation, like just Z variable, it's a linear regression. So this is just a weighted linear step. And then the second step is the sigmoid squashing function, which I already derived, e to the h over 1 plus e to the h. Okay, so we actually can represent this from a block type of representation. So we can put x1, x2, x3, and the pseudo variables. I mean, in this case, there are 3 features, and then plus a pseudo variable. Then we can just write the first summation, and they're just feeding into the summation, the round circles, which exactly shows you this W transpose X plus B operation. That give me the output is Z variable, and then the Z feed into the sigmoid function, which is a squashing or compression function. You can represent it as e to the Z, 1 plus e to the Z. And then this is exactly the output is from this sigmoid function. So the whole logistic regression can be represented as like 2 stage of operations, and then plus the input layer and output layer. All right, this is in fact exactly what we're going to represent the deep learning with. There's this dot product layer, if you still remember. Here I represent as a circle, and that's essentially a dot product operation, right? If you represent x as a pseudo variable, and we already did that exercise, so you can represent the whole thing as beta transposition x, right? It just, the one view emphasizes the differences of weights and bias. The other view, it just, okay, everything needs to be learned of that beta, and the whole operation is an inner product. All right, so the first is dot product, and then with a sigmoid, and you can then actually here, so from the y, I mean, this is your y predicted, right? And then you can also input the y truth, and the error, this error represent what type of loss function or cost function you use. And this whole pipeline gives you the loss output. And then you can take gradient and try to optimize the beta and the beta parameters in the whole thing. Specific E, what we use here is the negative log likelihood, which also is called cross-entropy in our setup, in this classification setup. And then because you have the loss and the cost, right, the E there, I mean, let's remember what we used in the stochastic gradient descent. And in the stochastic gradient descent, in there, we have this J theta, which is that MSE error in the regression. Our parameter is theta, so we try to use J theta, we try to minimize the J theta, and then to derive the theta through an iterative procedure, which is gradient descent. Totally the same in the logistic regression, and that's our error function is just negative log likelihood or cross entropy, and we just minimize that cross entropy, and then our parameter in this case, we just represent it as a W. We try to minimize it to push it to small, and through the same procedure, gradient descent. It's not going to theta, it gave me W. So that's really all it does. I mean, if you have a very, very simple one layer MLP plus a classification in the standard, in the state of the art pipeline, machine learning pipeline, deep learning pipelines, and you write it out as kind of block views, and you figure out the representation, figure out the parameterized layers and also non-parameterized layers. So the sigmoid function, if you remember, it has no parameters. Ez over 1 plus Ez. So in this basic version, it has no parameters. So that's why we normally call this type of layer. There's no non-parameterized layer. There are no parameters to learn. And the goal is to learn the parameters of those parameterized blocks through the loss, minimizing the loss. Same procedure as your homework one, you just use gradient descent. All right, so this kind of summarizes everything I want to talk about logistic regression. So logistic regression, in fact, it's on tabular data because I haven't explored anything about this two-dimensional grid structure, right? And the main goal is binary classification. Here I introduce you the fundamental, it's called a base classifier using the MAP rules. And the MAP rule, the most fundamental, is how do you model PC conditional X? And specifically for logistic regression, we model the P head because we model that output variable as a Bernoulli variable. And our P head in the logistic regression is this form, is this like E beta to this over E beta form, which actually is a sigmoid function. It's a sigmoid function on top of a linear regression formulation of input x. And the way we formulate the loss function is, in fact, is a maximal likelihood formulation. We maximize the likelihood, and it's equivalent to we minimize the negative log likelihood. There are different ways to solve it. You can solve by iterative Newton, which is a extract content. You can also solve it by stochastic gradient descent. And we're going to cover in next section about how do you evaluate the performance of a classification models. And I think this is all I want to talk about today.